I'm Larry Gladney. I'm a professor of physics at Yale University. Currently, I have two administrative roles in addition to being a professor, carries out research and teaching and service. I am Dean of Sciences for the Faculty of Arts and Sciences,
Oh, wow.
and I am Dean of Diversity and Faculty Development also for the Faculty of Arts and Sciences. I was an undergraduate at Northwestern University, and I did my PhD at Stanford.
Oh,
And
nice.
my research is experimental particle physics, but I have to preface that by saying that I don't do traditional particle physics. I work with telescopes. And so I work on questions of dark matter and dark energy, but using telescopes rather than accelerators, which is typically the way most high energy physicists or particle physicists do their research.
Yeah, and then on that topic, do you mind explaining a little bit more about your research, but in terms that are like understandable to a high schooler?
Well, basically, we understand that the world is made of atoms and that atoms are made of still smaller things like electrons and protons and neutrons. And then throughout the 1970s, we kind of discovered that protons themselves are made of still smaller things called quarks.
Oh, okay.
And we don't yet know whether there are things that are smaller than quarks that make up quarks, or if there are things that are smaller than electrons that combine together to make up electrons. Right now, we don't have any evidence that they are, but it's very difficult to imagine that we would have particles that have no size, that they are completely point-like. And consequently, there's been this push in the field of particle physics to try to discover whether there are more fundamental elements that make up the universe or not. And the question of how to best do that is where my current line of research comes in. Because with accelerators, we've tried and tried and tried and tried to find other more fundamental particles and failed to do so. But in astrophysics and cosmology, which is the study of the universe itself, we have pretty good evidence from what we observe of what the leftover from the Big Bang gives us, that there are, in fact, two forms of materials, if you want to call them that, which have not been found in accelerators. That's dark matter is a particle, and what we call dark energy. It may not be a form of energy, but it is some type of force that seems to be pushing things apart and making the universe get larger at a faster and faster rate. So I took that as a hint that accelerators are not getting the job done because there are two fundamental things that make up, in fact, about 95% of the universe's weight by mass. And we haven't seen either of them in an accelerator. And it didn't seem to me, say 20 years ago, as though we were likely to do so. Well, one way to study them is to look at their effect on the universe as a whole. So the universe itself is the laboratory. So we see how it grows and how the rate at which it grows has changed over time. And that allows us to infer some things about the behavior of dark matter and the behavior of what we call dark energy.
Oh, okay. That's really cool. And I remember learning about dark matter, I want to say like 2 or 3 years ago, and being absolutely like mind blown because like my entire life I was taught like the universe is matter, like we're all atoms. But then there was this like completely new topic that came in.
Right, exactly. It's fascinating stuff. So
Yeah.
obviously, a lot of people are interested in it, but the fact that we haven't been able to produce it in the laboratory makes it really hard to study scientifically. And so using the universe as a laboratory is an idea that came about 20 years ago. So right about the time when I made the switch away from accelerators. But those experiments take about 2 decades to build. So it's
Oh, wow.
about this long until we're getting to the point where the experiments are just getting finished and able to take data at the rate that we need. And we have the mathematical techniques to actually understand the data because we're talking very, very large amounts of data.
Yeah.
And the ability to combine those two, which is to actually get the data and then to be able to study the data, is something that's taken more than 20 years to actually get it all together working.
Yeah, and then talking about the timeline, where do you see your field expanding to in the next 5 to 10 years? And like where can students focus their attention to?
Well, for the next 10 years, I would say that there are two places. So it is true that we are not able to extend the reach in energy that we can get to with accelerators by very much. We have to build new accelerators, not simply sprucing up the ones that we have, but we can spruce up the ones that we have to put out more data. And so we can look more thoroughly at things that are maybe hidden in the noise of all of the particle collisions. I don't know how effective that's actually going to be at producing anything that's really fundamentally new, but you have to look. As scientists, you never make assumptions, you just do the experiments. The place where I really think that we're going to make great progress, though, in the next 10 to 20 years is with astrophysics and cosmology. And that's because we are adapting some of the techniques in building the experiments that we used in particle physics to astrophysics and cosmology. So those are now big science fields. They used to be done by very small groups of scientists. Now there are hundreds who are putting their talents in terms of engineering and technical procedures and scientific impact all together in a concerted push. Right. And so you've got basically a lot of very smart people who are all working towards the same set of goals. That hasn't happened before in
Oh,
this field.
wow.
So I really think that that's probably the most likely place where we'll see stuff that's really surprising. And it's true that technology is advancing very quickly. For example, we have new electronics, we have AI, machine learning, which is a subset of AI, has actually been much more effective than we guessed at actually pulling out new signals from data that human beings have not been able to, after scouring it, been able to actually see that there are some very subtle patterns that computers can actually pick out that human beings just can't, just given the scale and the scope. So all those things are very promising for saying that the next set of data taken with the new technologies is actually going to essentially be a new window on the universe. There's also the very interesting thing that came out in 2015, which is the discovery of gravitational waves, the experimental discovery. We were pretty sure that they existed theoretically, but the fact that we can now see them with instruments that we built means that we can now use gravitational waves as another way of illuminating what is otherwise invisible to us. Gravitational waves don't care about dust, for example, the way light does. They don't get blocked. They come from very, very early in the universe's history, unlike light, which got captured and scattered and re-emitted many, 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 many times since the time of the Big Bang to the time in which it was able to flow freely through space and come to us almost unimpeded. So gravity waves are maybe one of the more interesting ways in which we can probe both all of space and all of the history of the universe. And that wasn't really possible before the last couple of years.
Yeah, what's really cool is that like maybe like an hour or two before this, I had a meeting with a different professor at Vanderbilt, and he's actually studying gravitational waves.
Oh,
So it was
great.
really cool hearing about that. What drew you to the field of physics, and I guess in particular research?
Well, I can't really say. In my mind, I've always wanted to do physics, so there hasn't really been a time when I didn't want to do it. I've wanted to be a scientist, my relatives tell me, since I was 3.
Wow.
When they asked, what do you want to be when you grow up? But I didn't like science in grade school. It was just not for me. It was boring. It was messy. And
I
that's
understand
because
that.
you get biology and chemistry mostly. So I didn't really discover physics until I became 11, 12 years old. And as soon as I discovered what physics was, I knew immediately that that's what I wanted to do all along. That's really those were the kind of questions that I was most interested in asking. And, it takes a while before you learn that we've actually answered a lot of pretty basic questions. Why is the sky blue? Well, that question got answered more than a century ago. So it's really the case that, there were just a lot of answers already out there. Whereas when you look at biology, a lot of the basic questions that you want to ask, nobody really has a clue what the answers are or how we're going to do the experiments to actually find the answers. So physics just seemed a lot more approachable in the sense that we already know a lot. It's already a very ancient kind of, because it asks these very basic questions like what's the world made of? And so it's got history to it, which I'm really attracted to, things that have been long-standing questions that we've been trying to answer that go back basically to the beginning of when people were first writing down their thinking. And it connects to everything, right? So from the really very, very tiny to things the size of the universe itself, all of that's covered by physics.
Wow. Yeah, definitely. And then my next few questions are more geared towards high schoolers. So what
Mhm.
kind of skills can someone develop even without access to a wet lab that would, help them in the field of physics?
So the first is that one characteristic about most physicists, in fact, I would suspect all of them, is they are kind of voracious learners. And so you can use the internet to actually learn about an awful lot of things. When I was young, like after I just learned to read at 6 or 7 or something like that, I immediately started reading encyclopedias
Oh,
for fun.
wow.
And you just absorb an awful lot of knowledge because, again, physics covers such a wide range of things, right? There's no way in which you can be a specialist and expect that you're going to be very effective, right? You never know what connections there are between things that have been studied in this branch of physics that connects to this branch of physics or this part of mathematics that nobody suspected before you see that, oh, wait, there has to be a connection there. And I would say the thing that made Einstein most powerful, he was not the most powerful mathematician. Newton was a better mathematician. He was not the most careful physicist in terms of deriving theories. There were people that were much more cautious and careful about how they derived things, but he was extremely imaginative and very brave at connecting ideas that people thought, oh, they can't possibly have any connection between these two things. And he was really just, let me see if I can make a connection and let me see whether or not I can find a way to have these two ideas, hold them in my head long enough to get them to work. So, but you have to have those ideas. You have to know that,
Yeah.
right? Newton discovered the idea that gravity was the force that holds the moon around the earth because he had studied the ancient astronomers like Hipparchus, who had not only measured the fact that the moon orbits around the Earth, or they orbit around a common center of mass more accurately, but he had actually discovered the distance from the center of the Earth to the center of the moon. And Newton, because he was a very learned person, knew that, and in his head, supposedly, apocryphally, we don't know whether it really happened or not, watched an apple fall and calculated the rate at which the apple falls from the tree to the ground, and then tried to work out whether or not you could work out how fast the moon should fall around
Oh,
the Earth, and found that those two numbers worked out to be really close, as he says, pretty nearly. Now, he made a mistake in doing that, but in fact, it was the right answer, right? Despite the fact that he made the mistake. And so the question of having all this knowledge in your head allows you to connect, again, ideas that you don't know. So you do really have to read a lot, or you should be interested in reading a lot. The second is math skills are essential. And so you don't have, as I said, you don't have to be a great mathematician, but you do have to be very comfortable with using math as kind of a language, a way of explaining things. And then the third is that it's just increasingly important to be very comfortable and skilled with using computers.
yeah.
It's one of the things that we're teaching even graduate students now. I'm teaching a class, it just ended last week, but for graduate students in which we're trying to introduce them to computational techniques, but mostly to the idea that computers can expand and amplify your ability to do problem solving, but there's a very strong temptation to let them do the problem solving for you. And that's the thing that we have to avoid, that
Yeah.
human beings are really still essential, despite the fact that ChatGPT can write code. Anybody who's actually used it to try to write code understands that it makes subtle errors or it makes stuff up that's not true, typically doesn't know physics, right? And so consequently, it makes the kind of errors that if you simply just trusted it, you would actually, not make progress, and you might actually hold back progress by claiming things that are true that actually aren't. So I would say those three things, right? Just sort of read as much as you can, not all about physics, right? Like I said, any piece of knowledge might come in very handy. Get comfortable with using math, and then kind of get computer skills under your belt. I learned Fortran as a computing language in high school, and it was really very useful through me all the way through, right? Even though essentially nobody uses Fortran anymore. But the idea of learning how to make a computer or how to think in the way that a computer has to work in order to solve a problem has always been one of the most useful skills, I think, that I learned, despite the fact that you learn an awful lot of problem solving skills and you learn a lot of math.
Yeah, definitely. And I really agree with you on the point about like knowledge. Like I get asked this question like in interviews a lot, and I feel like I always respond with like learning things gives you like an arsenal of skills, and like you can pull out a weapon when you need it. But just
Mhm.
having it there, always at your disposal is always useful. And then my next question is, I'm sure you get a lot of cold emails from students, asking to join your lab. How do you pick someone out of a crowd? Like what makes someone stand out to you?
Well, pretty much the way that I got into working in physics, experimental physics. I knew I wanted to be an experimentalist, but when I went to college, you're just starting off as a first year and you don't really have the skills to start doing research. But I was on full financial aid, and as part of that, I was a work study student. And the list of work study jobs was pretty long, but most of them were really of no interest to me, like shelving books in the library or cleaning plates and trays in the dining hall and so forth. There was precisely one job that was actually in the physics department, and it was with the high energy physics group, an electrical engineer who was responsible for making a lot of the detectors that went into experiments at Fermilab from Northwestern. And so I thought, this is great. Nobody's going to be interested in that job. And when I arrived, I was the last in line behind a pretty long line. And when I got in, the interview didn't last very long because I didn't know how to answer any of the questions like, can you solder? Can you program a computer? Can you design electronic circuit boards? Do you know how to use an oscilloscope? No, 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 no. And I left with the head engineer saying, I'll call you.
Oh,
And of course, I was very disappointed at myself because I hadn't really even started physics classes, but I had already been deemed a failure, right? Not worthy of working even in a work study job with a high energy physics group. But after almost a week, I got really upset that, in fact, he said he was going to call and he never did. And so took every ounce of bravery I had. I went back and knocked on the door. And as soon as I stuck my head in, he says, "Oh, it's you. I guess you're ready to get started." And I said, "No, you said you would call me." And he said, "Well, let me tell you, there are things that I can teach people and there are things that I can't teach. Everything I asked you, I ask of every student that comes in the door, and none of them know how to do any of that stuff. You're all first year students. Right? Those are all things that I can teach. But for the things I can't teach, I tell everybody, I'll call you. And I never call anybody, but I do hire the first person who comes back."
oh wow.
And I thought, well, that's crazy. But it became very clear to me that if you're going to do anything in physics, you are going to be in a situation where the answer is not in a book. It hasn't been worked out by somebody else. You can't just go and ask an expert and they'll tell you, oh, here's exactly what you need to do. It's research. So the first job I got was building planar drift chambers for a new experiment that was going to happen in two years from the time I entered at Fermilab. And of course, I had no idea what a drift chamber was, let alone how to build one. And the only answer to how you make it happen is you think about it, you ask people, they give you a little bit of information, you put that information together, and you keep at it. You just keep coming back until you figure it out. And that is the way everything happens in research. If you don't have that kind of stick-to-itiveness, that kind of grit, then in fact, you won't make it in the field because most people will be working on their thing that they don't know how to do as well, right? And so they can give you a little bit of help, but they can't actually do it for you. So I apply that to the same kind of decision making about what students are really worthwhile to spend time with. And so if they send me an email and say, here's my resume, and I'm really interested in your research, I read about it on the website. You're right, I get a lot of those emails, and very, very seldomly do any of them write back and say, well, look, I'm still very interested. Now, most of that might be that they get jobs elsewhere, and that's fine. But really, it's sort of like the one thing that I think was really important for me to learn is that sticking to it, being very determined, not letting anybody tell you you can't do it is kind of key to making your way through certainly the hard parts of graduate school, right? I mean, there are very enjoyable parts, but there are some that are really very challenging because one of the things you learn in graduate school for which you're getting your PhD is how to do things that you didn't know you could do. And that part of it, really, people just have to discover. They can't be told
Yeah.
it. And no matter how many times people, adults tell you, you can do anything you want, you can be anything you want, you don't really believe it until you actually do something that surprises yourself.
Yeah, and then so I joined a wet lab recently, and we work with C. elegans, there's like little worms.
Mhm.
And so I went into the lab second week in, accidentally killed all of them in an experiment. And so, it was like it was constant repetition. And like I didn't realize research was a lot of failure. Like I feel like I read papers and like, it works out for everyone. But yeah, it's definitely a journey. And then do you have any more advice for high schoolers? Anything else that you'd like to add?
I would say one thing is to not be impatient, right? There's a lot of time to get involved. I know that these days people feel as though you got to rush, you got to get to the end point, and you got to know exactly how to take a path that gets you from where you are to where you want to eventually end up. Almost no one who winds up being a research physicist takes a straight path. I mean, I think it's very well worked out how to become a doctor. It's very well worked out how to become a lawyer. And it's still the case that a lot of people take diversions, they stop college and they work in a restaurant and then they come back to doing law school. My own daughter, on her way to becoming a lawyer, which she never thought about doing, was to be a bike messenger after she graduated college for a year. And so really, it's kind of, as you say, it's the journey, but you can't really know the journey, no matter how many experts you ask. Your path is always going to be a little bit unique and sometimes a lot unique. And the question of how do I get there? Well, again, you just sort of have this goal in your head, but the goal is not, I'm going to go to Stanford, right? The goal is I'm going to get a PhD in physics. And no matter where that happens, you can learn things along the way that give you very unusual opportunities. And the other thing I say to them is that, to high school students, is that there's this belief that you have to be a genius or you have to be really smart, you have to be mathematically gifted or something. And none of that is really true. And so when I went to start at graduate school, the two really smartest people in my graduate class, one did get his PhD, the other one never got his PhD.
Oh,
The one who did get his PhD, I asked people, can you guess what he's doing now? And nobody can. He just retired as a professional ballroom dancer.
wait,
So,
really?
yes, really. Yes.
Oh,
So
wow.
people's lives take very interesting journeys, but they're all individualized, they're all independent. He found, like decades ago, that really he preferred dancing to doing physics, and he was very, very good at it and very smart, but that just wasn't the kind of skill set that made for a successful career by itself, right? So yes, people are smart, but the level of intelligence really doesn't have to be that great to be really good at doing physics. But you do have to have this grit, and you do have to be able to convince people. You have to communicate well. You have to be able to convince people to follow your lead. But those things come with time. And so most of the students, I think, who are at the high school level, maybe they can see that in themselves, but most can't. And so
Hmm.
I really think the impatience of, it's going to be obvious that I'm going to make it, or if I'm not really sure, I should do something else, is typically where a lot of people fall off the path towards physics. And I think particularly a lot of girls fall off because they don't see a lot of role models, and they
Yeah.
really sort of don't think that there's anyone to kind of show them the path of how to be successful.